A scalar field is a function that assigns a single number to every point in space. For example, temperature T of x, y, z, or altitude h of x, y. The gradient of a scalar field f, denoted del f, or grad f, is a vector that tells how fast and in which direction f changes most rapidly. In three-dimensional Cartesian coordinates, del f equals the vector of partial f over partial x, partial f over partial y, partial f over partial z. Each component is a partial derivative, that is, the rate of change of f when we move only along one coordinate axis while keeping the other coordinates fixed. The gradient is a vector field. At every point x, y, z it gives a vector. Notation, you may see grad f, del f, or df, the differential. In engineering notes, the arrow notation vector del f is also common. Imagine a hilly landscape where the height is given by f of x, y. If you walk on a contour line, also called level curve, the height does not change. All points on that line have the same value of f. In three dimensions, the analog is a level surface f of x, y, z equals c. The gradient at a point points perpendicular, normal to the level surface passing through that point, and its length equals the steepest slope you could experience there. Analogy, think of a marble placed on a smooth bowl. The direction the marble would roll fastest is exactly the direction of the gradient of the bowl's height function at its location. The bowl's contour lines are the level curves. The marble moves straight out of the curved line because the gradient is orthogonal to it. Cartesian as given above. Nabla f equals partial f over partial x, partial f over partial y, partial f over partial z. Cylindrical r theta z, the unit vectors change with position. The gradient becomes nabla f equals e hat r times partial f over partial r plus e hat theta times 1 over r times partial f over partial theta plus e hat z times partial f over partial z. Example for f of r theta z equals r squared cos theta. Nabla f equals e hat r times 2r cos theta plus e hat theta times negative r sin theta, divided by r equals 2r cos theta e hat r minus sin theta e hat theta. Spherical rho phi theta, with rho radius phi polar angle 0 at north pole, theta azimuth. Nabla f equals e hat rho times partial f over partial rho plus e hat phi times 1 over rho times partial f over partial phi plus e hat theta times 1 over rho sin phi times partial f over partial theta. If f of rho phi theta equals rho sin phi, then nabla f equals e hat rho sin phi plus e hat phi cos phi divided by rho. These formulas are memorized by engineering students. They follow from expressing the differential df in the corresponding basis. The directional derivative of f at a point p in the direction of a unit vector u, denoted d sub u f of p, measures the rate at which f changes if we move away from p a tiny amount along u. d sub u f of p equals limit as h approaches 0 of the fraction f of open parenthesis p plus hu close parenthesis minus f of p over h. If f is differentiable, the limit exists and can be computed with the gradient. d sub u f of p equals nabla f of p dot u. Thus we simply take a dot product of the gradient vector, which contains all partial rates, with the direction vector. Step 1, find the gradient of f. Step 2, evaluate it at the points. Step 3, make u a unit vector, divide by its magnitude. Step 4, compute the dot product. Real-world example. If T of x, y, z is temperature, d sub ut is the temperature change per meter you would feel if you walked straight northeast, the chosen u. Because d sub uf equals norm nabla f times norm u times cos theta, where theta is the angle between nabla f and u, and norm u equals 1, we have d sub uf equals norm nabla f cos theta. A consequence is, the maximum directional derivative occurs when theta equals 0, that is, when u points in the same direction as the gradient. The maximum value equals norm nabla f. The minimum, most negative, derivative occurs when theta equals pi, that is, opposite the gradient, giving negative norm nabla f. Directions orthogonal to the gradient, theta equals pi over 2, give a derivative of 0. Moving tangentially along a level surface does not change f. This geometric picture helps students quickly decide which direction gives the steepest ascent or descent. Explanation: chain rule for directional derivatives along a parametrized curve. Suppose a curve R of t equals open parenthesis x of t, comma y of t, comma z of t close parenthesis, passes through the point P at t equals t sub 0. The rate of change of f along the curve is the total derivative d over dt f of R of t, evaluated at t sub 0. Using the chain rule, d over dt f of R of t equals nabla f of R of t dot dr over dt. If we set u equals dot r of t sub 0 over norm of dot r of t sub 0, the unit tangent to the curve then, d over dt f equals norm of dot r of t sub 0 times d sub u f. Thus the directional derivative is the instantaneous change per unit length along the curve, while the chain rule gives the change per unit parameter t. Example: temperature along a road R of t equals t, 2t, 0 at t equals 1, where t of xy equals x squared plus y squared. Compute nabla t equals open parenthesis 2x, 2y close parenthesis. At t equals 1, r equals open parenthesis 1, 2 close parenthesis. Nabla t equals open parenthesis 2, 4 close parenthesis. Dot r equals open parenthesis 1, 2 close parenthesis. Chain rule: dt over dt equals open parenthesis 2, 4 close parenthesis dot open parenthesis 1, 2 close parenthesis equals 2 plus 8 equals 10. Explanation: typical exam type problem, finding the gradient and directional derivative at a given point. Problem statement: let f of xyz equals x e to the yz plus ln of 1 plus x squared. Find a nabla f. B. The directional derivative at point P of 1, 0, pi in the direction of vector v of 2, minus 1, 2. Solution outline. Step 1: compute partial derivatives. F sub x equals e to the yz plus 2x divided by 1 plus x squared. F sub y equals xz e to the yz. F sub z equals xy e to the yz. Hence nabla f equals the vector of e to the yz plus 2x over 1 plus x squared, xz e to the yz, xy e to the yz. Step 2: evaluate at point P where x equals 1, y equals 0, z equals pi. E to the 0 equals 1, 2 times 1 divided by 1 plus 1 equals 1. So nabla f at P equals the vector of 1 plus 1, 1 times pi times 1, 1 times 0 times 1, which simplifies to 2 pi 0. Step 3: unit vector in the direction of v. The norm of v equals the square root of 2 squared plus negative 1 squared plus 2 squared, which is square root of 9 equals 3. U equals 1/3 times the vector of 2, minus 1, 2. Step 4: directional derivative. D sub u f at P equals nabla f at P dot u, which is the dot product of the vector 2, pi 0 with 1/3 times the vector 2, minus 1, 2. This equals 1/3 times the quantity 4 minus pi. Marks allocation: part A 3 marks, differentiate each variable, part B 2 marks, evaluate at the point, part C 2 marks, normalize v, part D 3 marks, dot product and final answer. Total 10 marks. Let S sub c be a level surface, defined by f of x, y, z equals c, where c is constant. Consider a smooth curve R of t that lies entirely on S sub c, so f of R of t equals c for all t. Differentiate with respect to t. D over dt of f of R of t equals nabla f of R of t dot r dot of t equals 0. Because the derivative of a constant is 0. At a specific point P, r dot of t sub 0 is any tangent vector to the surface at P. The dot product being 0 for every tangent vector means the gradient vector at P is perpendicular, normal to the tangent plane, that is, orthogonal to the level surface. Key point: the argument uses only the chain rule, and the fact that moving along the surface does not change f. Common pitfalls and quick tricks for evaluating directional derivatives in exams. Pitfall: forgetting to normalize the direction vector. Why it happens: the formula d sub u f equals nabla f dot u assumes u vector is a unit vector. Quick fix: always compute norm of v vector first and write u vector equals v vector divided by norm of v vector. Pitfall: mixing up order of partial derivatives. Why it happens: some students write partial f over partial x as partial x over partial f. Quick fix: remember the derivative operator acts on f, not on the variable. Pitfall: using Cartesian gradient formula in cylindrical or spherical problems. Why it happens: the basis vectors change with position, leading to missing 1 over r or 1 over rho sin phi factors. Quick fix: write down the appropriate gradient formula for the coordinate system before differentiating. Pitfall: assuming the gradient points uphill in all directions. Why it happens: gradient gives the steepest ascent, other directions can be uphill, downhill, or flat. Quick fix: use the angle formula d sub u f equals norm of nabla f cos theta to judge sign. Pitfall: not checking the domain of logarithms or square roots. Why it happens: functions may be undefined at the evaluation point, causing loss of marks. Quick fix: verify the point lies inside the function's domain before differentiating. Trick: if the question only asks for the maximum directional derivative, you can answer norm of nabla f without computing any dot product. Key formulas: gradient Cartesian equals nabla f equals open parenthesis partial f partial x comma partial f partial y comma partial f partial z close parenthesis. Gradient cylindrical equals nabla f equals e hat sub r times partial f partial r plus e hat sub theta times 1 over r times partial f partial theta plus e hat sub z times partial f partial z. Gradient spherical equals nabla f equals e hat sub rho times partial f partial rho plus e hat sub phi times 1 over rho times partial f partial phi plus e hat sub theta times 1 over rho sin phi times partial f partial theta. Directional derivative d sub u f equals nabla f dot u equals norm nabla f times cosine theta. Unit vector u equals v divided by norm v. Chain rule along a curve d over dt of f of r of t equals nabla f of r of t dot r dot of t. Orthogonality proof: nabla f dot t equals 0 for any tangent t on f equals c. Typical marks distribution: 10-mark question. 2 marks: write the correct gradient formula for the given coordinate system. 3 marks: compute all partial derivatives correctly. 2 marks: evaluate the gradient at the specified point. 1 mark: form the unit direction vector, show magnitude calculation. 2 marks: perform the dot product and present the final directional derivative. Quick checklist for exam day. Step 1: identify the scalar field and the coordinate system. Step 2: write the appropriate gradient expression. Step 3: differentiate, watch for product chain rules. Step 4: plug in the point. Step 5: normalize the direction vector. Step 6: dot product gives answer. Step 7: check unit sign and whether the answer makes physical sense. For example, maximum derivative should be positive. These points, together with the analogies and pitfalls above, give you a solid roadmap to score full marks on any gradient directional derivative problem.